Hi, it's Mr. Anderson, and this is Chemistry Essentials video 27. It's on molecular, ionic, and net ionic equations. And so in chemistry, you should be able to observe something. So let's say watching of a Bunsen burner, figure out what are the chemicals that are combining in that reaction, write out a balanced chemical equation, and then depending on what kind of a reaction we're looking at, you may want to use a different type of equation. And so let's start with the combustion of methane. And so what comes out of a Bunsen burner is going to be methane gas. It's CH4, so 1 carbon and 4 hydrogen atoms. It's going to combine with oxygen, which is going to be 2 oxygen atoms in an oxygen molecule. And then we're going to get combustion. And so what is yielded in that reaction? We're going to make carbon dioxide and water. And so that's what this arrow stands for. Now, if you look at this, the thing that should jump out right away is I don't have enough hydrogens on the right side compared to how many I have on the left side. And so what I could do is I could add another water on the right side. I'm trying to balance it. And now when I look at it, well, I'm good on the hydrogens on either side, but now I've got too many oxygens on the right side, so I could add another oxygen molecule on the left side. Now we have a balanced chemical equation. We're just looking at the particulates here. And what does this mean? In combustion of methane, 1 mole of methane is going to combine with 2 moles of oxygen to make 1 mole of carbon dioxide and 2 moles of water. We have a balanced equation. And so in chemistry, you should be able to go from observing something, kind of writing out the particulates, going to an equation, and then starting to utilize that. And so when you have chemical change, remember what's happening is we're breaking bonds and forming new bonds. What we can do is we can write a chemical equation that represents that. It has to be balanced in order for it to be useful, especially when we're looking at stoichiometry. And so a general equation of that is going to be a molecular equation. That's the kind of chemical equation you've used your whole life. But there are 2 other equations that are important. One is a ionic, and sometimes we call it a complete ionic equation. This is most important when we're looking at ions dissolved in solution or in aqueous reactions. And then there's something called a net ionic reaction. What that allows us to do is really just look at the atoms that are important in that equation, and that'll also become important when we're looking at redox reaction. But all of these equations, we should be able to go back to that particulate and really understand what's going on in a chemical reaction. And remember, chemistry is a laboratory science, and so you should be able to observe something in the laboratory and then come up with one of these equations for it. Now, a great way to look at balancing equations is on PHET. And so what you can do is you can go there and you can actually set up balance scales of the atoms. So here we're looking at making ammonia. I can add 1 of each of these, 1 mole of each of these, and I can see that it's not balanced. On the left side, I have too many nitrogen. Now I can balance it with hydrogen. And you can see I get a smiley face because I've balanced the atoms on either side. And so remember, you can't change the molecule, but you can change the coefficient in front to balance it. Now we've got water. So I didn't have enough oxygen on the left, and now I balanced it with hydrogen on the right side. Or if we're looking at combusting methane, I add 1 of each, and then I find that I don't have enough hydrogen on the left side, so I can balance that, or on the right side, and then I can balance my oxygen out. What's fun about this is once you think you got it, you can go to a balancing game where it'll serve really different equations at you. Some are going to be really easy, some are going to be hard, and then you balance it. And when you think you got it right, then you can check it. And then if you're right, it'll give you the smiley face, and you can go on to the next one, and it's going to time you, and so it's a lot of fun. So balancing equations is important, and it's a step that you always want to do when you're looking at any equation. And so let's go back to this Bunsen burner again. So the first thing you're going to do is observe it. Next thing you're going to do is try to describe what happens. So methane is combusting in the presence of oxygen to create carbon dioxide and water vapor. We then write the reactants and the products, and that arrow stands for yields. Next thing we do is we balance it. So we can write coefficients in the front to make sure we have the right amount of atoms on either side. And then the one thing that we should also include on a nice equation is what state it's in. And so in this reaction, we have gases combining to create carbon dioxide gas and water vapor. And so now we've got a molecular equation. And now we can use it to do stoichiometry, for example, and to make measurements. But now let's go to an aqueous reaction. And so in this reaction, we're taking lead nitrate, which is clear, and we're adding it to a solution of potassium iodide, and it produces a yellow precipitate. And so what we're getting is a solid that comes out of that. And so I could observe that. I could know what those chemicals are, and then I'm going to write it out. And so we've got a solution of lead nitrate, solution of potassium iodide, and it's making a yellow precipitate of lead iodide that settles to the bottom. Next thing I want to do is I want to write out my reactants and products. Now, if you don't know how to go from the name of a chemical to its equation and vice versa. I'll put a link down here to a naming molecules or a naming compounds video that should help out. So the first thing I want to do is I want to write out all the reactants and products. So now we've got lead nitrate, potassium iodide, making lead iodide and potassium nitrate. Next thing I want to do is I want to make sure that I balance it. And so I can see right here that I don't have enough iodine on the left side, so I could add a 2 there. Now I've got too many nitrates on the left side, so now I could balance it like that. I also have to write the state that it's in. So remember, those first two were aqueous, but this lead iodide is going to be a solid. And now I've got a nice molecular equation. But again, this video is about two other equations. We've got ionic equations and then net ionic. And so how does that work? What is an ionic equation? Well, if you think about this lead nitrate right up here, it's not sitting in that solution as a connected molecule. Remember, it's going to break apart into its ions. It's going to have its lead ions and nitrate ions, and those are going to disassociate from one another. Those are going to separate from one another. And so when I'm writing out an ionic equation, what I have to do is I have to write out all the ions. And so let's do that one first. I'm going to have that lead ion, which has a 2+ charge, and then 2 of those nitrates, which have a 1- charge. Now, why am I writing a 2 here? Because we have 2 of those nitrates. And so you can see in an ionic equation, what I'm doing is I'm busting apart each of those ions. Let's go to the next one. So that potassium iodide, I'm going to break that apart into its 2 ions as well. You can see that I'm writing that this is in solution, so it's aqueous. Next, we get to the lead iodide. Now, remember that lead iodide is a solid. It's that yellow solid. And so I'm not going to bust that apart into its ions. I'm just going to write that as lead iodide as a solid. But then this potassium nitrate is going to break apart into its different ions, so I'm going to write it out like that. So I know that's a lot of work, but this is a complete ionic equation. Why is that important? It really allows us to look at what ions are in that reaction. And so if it's ever an aqueous reaction, lots of times we'll use this ionic equation. Sometimes they'll call it a complete ionic equation because it's showing all of the ions that we have present. Okay, what's the third type of equation? That's going to be the net ionic equation. So if we look back at this equation, you can see that we have 2 nitrate ions on the left side, and we also have 2 nitrate ions on the right side. And so they're really not being changed in this reaction. And so we call those spectator ions. They're really just watching. And so what you can do is you can cross out things on the left side that are also found on the right side, as long as they're in the exact same form. Can you find something else on the left side that's also on the right side? That's going to be those potassium ions. So I could cross those out as well. And so once I've crossed out all those spectator ions, I can write it out like this, and that's going to be my net ionic equation. So that's really, it's just showing what atoms are part of this chemical reaction that are actually forming these bonds. And this will become important when we're looking at redox reactions in the front. So now once you've got those equations, so this would be a molecular equation, then you should kind of be able to work back to those particulates. And so let's write out the ionic equation just using symbols, using those diagrams rather, using those molecules. And so we have lead and nitrate ions. This is what they're going to look like in solution. Remember, they're not connected, they're dissolved in the water. Next, we're going to have the potassium and the iodine. So those are going to be separated as well. This is going to be the iodine, or the big purple spheres, and the small purple spheres are going to be the potassium. And now we're going to have a reaction. What does it look like after that? Then we're going to have the nitrate and the potassium ions. Again, those are spectator. They didn't change. Then we've got the lead iodide. You can see that's that yellow solid. And so this is really what we're representing in an ionic equation. And then in a net ionic equation, what it's showing us is that we just have those lead and iodine ions that are combining together to form that lead iodide. And so that's going to be a real simple form of that. So did you learn to translate an observed chemical change into a balanced equation of the correct type? Remember, there are 3 types. Molecular is the one you're familiar with. Ionic is when we're breaking it apart to show all the different ions. Net ionic, however, is when we're just showing the atoms that are part of that chemical reaction. And I hope that was helpful.